Alrighty, y'all. Today we're taking a look at question 2 for homework 5. And this one has parts A, B, and C, and I'm going to go through all 3 of those in this video. Alright, so we have this complicated mess of a structure. And for part A, we're trying to find the magnitude and the direction. We're trying to find the magnitude and direction of the current I2 so that the net magnetic field at P over here is 0. Right, so we have 2 wires in total, and our magnetic field at P we want to be 0. Right, so if they're going to be 0, right, if we do our right-hand rule real quick, this one's going into the page, so it's going to be going clockwise. This one's coming out of the page, so it's going to be going counterclockwise. Right, so based on that, on this side's going to go up, this side's going to go down, just as a tangent line to that circle. Right, this one's going to go down, this one's going to go up. Right, so over at P, off to the right of this one and off to the right of this one, up and down, it can cancel, and it can cancel to 0, right? So for it to cancel to 0, they're going to be equal in magnitude, right? Equal and opposite, since they're going in opposite directions. Right, so our magnetic field, as always, B equals mu naught I over 2 pi r. Right, so for our first wire, distance to P is going to be 1 meter plus our 1 meter plus our 0.5 meters, 1.5 meters. Right, so we have our mu naught, and our I for the first one is 6 amps. Mu naught times 6 over 2 pi 1.5 was what I just said. Yeah, that's what I just said. All right. And that's our magnetic field from the first wire. Now we're setting that equal to the magnetic field from the second wire. Right? So that's going to be our mu naught. And we don't know our second current, I2, so that's just going to be a variable, over 2 pi times our radius, right? Our distance from I2 to P, which is just 0.5 meters. Right? So now we do some rejiggering. We can divide both sides by all that mess and cross multiply, zip, zap, zop. We get our 6 times 0.5 is 3 over 1.5 equals I2. All right, and 3 over 1.5 is just 2, so I2 is going to equal 2 amps. Again, everything we kept in base units with meters and amps, so our final answer, 2 amps, right? And I kind of spoiled it. It did say what must be the magnitude and direction. I just assumed right off the bat that it was coming out of the page, right? But the check that I did was how you would determine that, right? Because if they were both going into the page, this one would be going clockwise, this one would also be going clockwise. So the same thing on this side, tangent line would be going down, this side the tangent line would be going up, side tangent down, tangent up. Since if they're both going in the same direction like this, the only place that it could cancel and go to 0 would be in the center, in between them, when one's going down, one's going up. Because otherwise they would either both be going down or both be going up, right? So our direction is 2 amps, and it's going out of the page. I can draw that in there, okay? Cool. Now on to part B. All right, what is magnetic field at Q? So this one, we're assuming that our math from the first one was correct, which it was. I promise you it was. So now we're just trying to find the magnitude of the net magnetic field at Q. Right, so same thing, right? This one going into the page, going clockwise. This one's going counterclockwise, it's coming out of the page. That is a god-awful looking arrow, right? So we know that on this side, this one's going to be going up, and this one, right? Our magnetic field from this, at this point, is going to be going up because it's to the left. This one's going to be going down because it's to the left as well. Right? So we know that our first one, our magnetic field from this first wire is going to be our positive, and this one is going to be our negative, right? So let's take a look at that. All right, so we're using our same equation as always. B equals mu naught I1 over 2 pi R1. And I'm just marking it with the 1 because that's just going to be our first wire. All right, so our magnetic field from the first wire, all right, we have a radius. Our distance to our Q is this 0.5 meters, and we have a current of 6 amps. All right, so we have our magnetic field from the first wire. It's going to be, again, our mu naught is 4 pi times 10 to the negative 7th. I'm just going to cancel that out, divide by the 2 pi already. So I'm just going to simplify it to 2 times 10 to the negative 7th times our current, which is 6, over R1, which we said was 0.5 meters, right? Cool. Now we're going to do the same exact thing, but we're just going to solve for our, oop, don't do that. We're going to do that for B2, right? Same thing, our coefficients, our constants, they still cancel down to 2 times 10 to the negative 7. Our current, what we calculated before, is our 2 amps, right? 2 amps divided by our radius here, which is going to be 1 plus 0.5, and our 1 plus 0.5, 1.5, right? And that's going to give you your B2, right? B1, B2. Now to get our net magnetic force, we're just going to add them together. But remember we said that this one is going counterclockwise, this one was going clockwise, right? So over here, this one is going to be positive, and this one's going to be negative, right? Because it loops around, goes down there. All right, so it's going to be B1 minus B2, and that's just going to give you your B total, right? And that's going to give you your total magnetic field for that one, right? Cool, great, lovely. Part C. This is my personal favorite because it is, right? So here we have to do our same exact thing. We have to calculate our magnetic field for our point S up here, which this one's a little bit more complicated only because it involves directions and stuff, right? Because before everything was just, our tangent lines were just going perpendicular. Don't move the picture. The tangent lines were just going perpendicular, so they just added perfectly with each other. But now, since it's off on this angle, we get to do some more trig, right? So what we're going to start with, we're just going to start by finding our magnitude from each of them, right? So our first wire, our B1, our magnitude of B1 is going to be, again, our mu naught I1 over 2 pi R2. Oop, R1, sorry. Too many 2's. Right, so our B1. Again, I'm just going to cancel this down because it's easier for me to think about and look at. 10 to the negative 7 times our I1, which was 6, divided by 2 pi R1, our distance from our wire to our S, 0.6 meters. Ooh, I wrote all of that wrong. I'm sorry. The 2 pi canceled out when I wrote this as that. So 0.6 is there. All right, so there's your B1. All right, and now we get our B2. Same exact equation. Our mu naught, again, our mu naught divided by 2 pi is going to cancel to 2 times 10 to the negative 7 times our current, which we calculated in that first problem, still our 2 amps, divided by our radius, which again, our distance between the two is this 0.8 meters right there. And that's going to give you a magnitude of B2. All right, so now we get to do the fun part and find our directions. Right, so for our B1 direction, that's just going to be whatever our magnitude is of B1 times, well, this one with our horizontal here. Right, so all we're looking at, right, our circle, here's our radius. If we're looking at this triangle, fun fact, these are all multiples. If you divide similar triangles. I'm doing a similar triangles thing, right? Divide this, it's a 3, 4, 5. I don't know how the math actually works, but you can see it's a 3, 4, 5 because they're all times 2 but also divided by a mass. You get it. 3, 4, 5. We all remember that. Similar triangles, which means this is a right angle, right? So which means that when I draw my circle, right, whenever my circle for this one, it goes clockwise all the way out here, any tangent line is going to be perpendicular to the radius, right? Cool, lovely, great, right? So that means that our tangent line here, perpendicular to the radius, is going to be going on that same triangle, right? And then same thing for this one. Here's our radius, and now here's perpendicular to the radius, right? Because that's going, yeah, out of the page, going counterclockwise, right? So it's lovely that all of our vectors line up on this nice 3, 4, 5 triangle. So if we have our first vector, I'm just going to redraw this over here. All right, here's our 3 points just real quick. All right, so our I1 causes that B1. Here's our B2. Here's our 90-degree angle. All right, so they're 90 degrees to each other. Pretty dang cool. Since it's just adding... So I was going to break all of these into components and solve them out for components, but I just noticed something a lot more fun. We're only looking for the magnitude of the magnetic field, which means that forget breaking them into components. Our B1 and B2, if we're trying to find how they add together, all we're doing is finding the hypotenuse, right? Yeah, that's just going to be our hypotenuse of this triangle. The same way that if we had an x and a y direction, our hypotenuse of that triangle is our net force. Or our net vector, I guess. I keep saying force. Right? So all we have to do to add these two together is to treat them like a right triangle and square them both and take the square root, and that's going to give us our magnitude. It's not going to give us a direction, but it's a lot easier than breaking each of them into components and trying to figure it out that way, right? So all it is b1 squared plus b2 squared, take the square root, that's going to give your b total. Okay. All right, well, I hope you found this video at least a little bit helpful with all 3 of the questions. Or all 3 of the parts, I mean. Let me know if you have any more questions about anything that I did, or if you have any other problems that you want me to explain, and I will do my best to try to explain it, because I guess Sydney explains stuff.